Last time I assigned 4 problems to hand in tomorrow, right? This is correct, 18 to 21, for coming from this Wednesday, and then 4 more for next Wednesday, right? I'll put it on the web, right? Okay. Right, I think I'll back off and just repeat a bit of what I talked about last time. Just start from the beginning rather quickly, since perhaps a few more are coming. Just repeat the first parts of what I had talked about last time. And this lecture is to generalize the ideas of parallel transport, connection one form, curvature, and so on, to non-abelian gauge theories. Because some of this, as we shall see, we have already learned in the special case of abelian gauge theory, in other words, electromagnetism, right? So these are the topics we will cover. The idea of local vector spaces. Because they are local, the idea of parallel transport, and the concept of a covariant derivative and the connection one form. The first 3 dots we had sort of covered last time. I will repeat them very quickly today, and then come to the last 3 topics, connection and basis vectors, going back to the case of EM, and then looking at non-abelian gauge theory, which is, of course, a very important part of modern field theory, right? Right. So local vector space. If we start with the case of a complex wave function, the simplistic description is that a wave function is a mapping from a base space, B, to a vector space. And it is useful for generalization later to think of the complex plane as a 2-dimensional real vector space with the real dimension and the imaginary dimension. That's 2 different languages, whether you consider it as a complex number or as a 2-dimensional real number. It's the same thing. And I also emphasize that the base space need not be a vector space. The base space is just a set of space-time points typically, although mathematically it need not be, all right? So in the base space, there is the concept of coordinates, there is the concept of neighboring points, but there is not necessarily a concept of A, distance, B, of vectors, all right? These things we don't need for the base space. So that is the concept of a complex wave function. So we can represent this in another way, which will be convenient later on, that a wave function is just a mapping from a point x in base space to a vector psi in a 2-dimensional vector space. And since you have a 2-dimensional vector space, that means there are 2 basis vectors on the vector space, labeling the real direction and the imaginary direction. But we had earlier talked about the importance of allowing for the phase convention to be different at different points. That is, I can rotate the phase of a wave function, not just the same rotation everywhere, but I rotate by 1 degree here, rotate by 2 degrees in the next room. And we have seen in the example of EM that degree of freedom, allowing the phase to be locally defined, is intimately connected to the vector potential, A mu. And in fact, doing that you have to do the phase transformation at the same time as you do a gauge transformation on the vector potential, changing the vector potential by a gradient. The 2 are deeply related, right? And to generalize this idea, therefore, we look at the mapping in the following sense. If I am to change the phase convention at different points, that means I choose different real and imaginary axes as different points, right? So if I change the phase, that means I rotate the real and imaginary axis by a certain angle. Which then means that at a point x, here is the vector space with the 2 basis vectors. Here's the point x prime with the basis vectors, which may be different, okay? So this is the real direction on this vector space. That is the imaginary direction on that vector space. Now with that, it becomes convenient to think of the vector space not as one single vector space, and that is a very important mathematical generalization, but as one vector space for each point x on base space. and I just use the word a private vector space, which is in this case a C, for each point. Right? So the mapping, the wave function is not just one base space, one vector space, but one base space, many, many, many vector spaces. Right? So to generalize this to the case where the vector is not just a complex number, but a general n-dimensional vector. Right? So we now have a vector which is an n-dimensional thing. Right? So let me write it this way. Capital N is the dimension of the vector space. And now, what is a physical example where n is non-trivial? Would be, as we discussed, isotopic spin. Right? So it could be up and down isotopic spin. It could be n equals 3, three colors of quarks. Okay? So red, green, blue would be the 3 entries here. And in fact, each of these could be complex. It could actually be 3 complex numbers rather than 3 real numbers. So from the earlier discussion on internal symmetries, and internal symmetries just means, for example, SUN, you are free to interchange n different objects. Right? So we have the general possibility that the wave function is an n-dimensional vector. Right? So that is the amplitude of finding a red quark, the amplitude of finding a green quark, the amplitude of finding a red-blue quark. Okay? So you have a mapping from a base space, say 4 dimensions, space-time, to a vector space, which is n-dimensional. In the case of complex fields, it could be 2. In this case, it could be 3. So the idea now, we now consider a wave function of mapping from B to V, where again, V is a private one for each point, because we are now making a generalization. When we talked about symmetries, SUN symmetries, we meant we are free to do a linear transformation on these, mix these up, change red to blue and so on. But now we anticipate. Suppose we are later going to say we can change this convention differently at each point. So think of red, green, blue as 3 axes in some 3-dimensional abstract vector space. Red, green, blue, those are the 3 directions. All right? So I choose them this way here, and I choose them in a different direction here. So I just change red into blue, let's say. Okay? That is like rotating the red, green, blue axes. But since red, green, blue are not detectable anyway, because everything in the physical world is a color singlet, as we shall see later. Right? I am free to rotate the 3 axes, red, green, blue, but also to do this differently at different points. Okay? Now, so the concept of what you mean by real and imaginary is related to the phase degree of freedom. That could be local. Now we are talking about an SUN transformation where the convention is also local. I just move the SUN axes in a way which is different at each point. So therefore, I also have the concept that this n-dimensional space and that n-dimensional space may be different. The axes may be related by some linear transformation. Right? So that is the generalization of the local phase transformation. So in the EM case, that is n equals 2. We have talked about this. 1 and I you can think of as the 2 axes. And when that happens, what do you do with parallel transport? So very often we have to subtract 2 neighboring vectors. Now, here we are talking not just about vectors, but vector fields. That is a vector function, a vector defined at each point in space. So how do I subtract 2 vectors at 2 slightly different points? That's like taking a derivative, right? That's a derivative. So how do you take derivatives? And the key difference now is that these 2 vectors are on different vector spaces. So how do you do that subtraction? The way to do it is to move this vector over here to A prime by parallel transport, if you like, and actually you do the subtraction here, B minus A prime. So the key question of how to do this is how to move a vector from one plane to a neighboring plane. Right? Delta x always will be infinitesimal. And when you do parallel transport, of course, you want to keep the vector fixed, which is not the same as keeping the components fixed. And I'm not sure I did this last time. Suppose I use polar coordinates. And I have a vector here, say like this. When I do parallel transport, say to here, I transport it so that this vector is the parallel to that vector. But if I look at the components, no different colors. Okay, just have to use the same colors. This is purely radial. And this is the tangential direction. So this vector has 0 tangential direction component. Okay? But if you look at this vector, the radial vector is here and the tangential vector is here. So this vector, which is the parallel transport of this vector, has both a radial component and a tangential component. So the components are not fixed in parallel transport because the basis vectors may change from place to place. Okay? So how do we account for this change of components? The components get mixed up, slightly transformed because of this. And I think we got to roughly here in the following. First of all, when you push something by a certain amount, say delta x, this is what you do. That is just a Taylor expansion, just tells you that you change the argument of the function, right? So previously, when we were talking about a scalar function, we had something like this. I call it C here. So this is plus or minus, doesn't matter. So this. Okay, so that's just Taylor expansion. So if you can also write it in the exponential. That's just changing the argument. But now, the components has to be mixed as well, right? So although the vector does not change, you have to mix the components, do a linear transformation on the components. And the most general mixing of the n components is some n by n matrix, some linear transformation. But of course, what you do here, the mixing must depart only infinitesimally from the identity, and the difference from the identity must be proportional to the displacement. Okay? So this operator tells you how much you mix the components as you do this transformation. Okay? And it is convenient in comparison with this to write this also in exponential form. To first order, it doesn't matter. And what is gamma mu? Oh, sorry. You see, this is mixing the n components. So gamma mu is an n by n matrix. Okay? So this is an n by n. This whole thing acts on a vector like this. So this is an n by n matrix, but carrying an index mu. So if the base space has 4 dimensions, then there are 4 gamma matrices, each of which is n by n. Okay? N does not have to be equal to 4, can be anything. If I'm talking about the color group on ordinary space-time, then base space is 4 dimension, mu has 4 values, and n is equal to 3. Okay? So that is 3 colors defined on 4-dimensional space. So gamma mu is an n by n matrix. That means acting on a column vector, it can be represented with 2 other indices. So a particular gamma mu acting on the vector, its I component, is equal to these things multiplying the k component of psi, sum over k. So the ik indices, the English letters, are matrix indices. They go from 1 to n. Okay? So I, in particular, want to emphasize the difference between the 2 types of indices. Ik go from 1 to n. They are associated with the vector. Mu is associated with the base space, which can take a different range. Now, for those of you who have taken relativity, this will sound unfamiliar. In relativity, mu, the 2 lower indices, have the same type, right? They are even symmetric. Okay? But that is a special case. For a vector space, which in some sense is very similar to the base space. Now, in this example, the vector space has nothing to do with the base space. Base space is space-time. The vector space is color. Okay? So in general, the vector space does not have to be related to the base space. So you have three indices like this. And the convention is the following. So we have two transformations. We could multiply them together. That is, add the two things in the exponent. Because we are doing infinitesimal transformations anyway, doesn't matter. So often we will be dealing with real fields. So this is purely real object. So this is also a purely real object because you transform a real field to another real field. So in those cases, gamma mu is a real matrix. But we also have to keep things unitary. That is, when you mix the components, you have to preserve inner products. So in the same way as we discussed earlier, if you have e to the something, which is unitary, then what is in the exponential has to be anti-Hermitian. In other words, it can be written as I times a Hermitian matrix. Okay? So gamma mu is anti-Hermitian. Now, in the convention, we typically don't write I here. Okay? We rather let gamma mu be anti-Hermitian. That's because sometimes we deal with purely real fields, and therefore it is better to write gamma as without the I. So if it's, think of it as a matrix, it will be an anti-symmetric real matrix in those cases. And we will see an example of that later. All right, so that's where we were last time. All right? Now, so what I have given so far is just to suggest that there is the need for a non-trivial matrix gamma. I haven't told you what that gamma actually is. I haven't given you a representation of what that gamma is. All right? And now I'm going to do so. But just to give you some notation, gamma mu actually, we say, connects one vector space to the next vector space. Right? Because if I want to transport a vector from one vector space to the next vector space, I need gamma to provide that connection. So mathematicians call it the connection one form. Okay? And so to parallel transport a vector, what you need to do is this thing, which I write together as capital D mu, and capital D mu is this combination. Because when you transport a scalar, all you need to use is the derivative operator. That is what happens in the Taylor series, right? But when you transport a vector, the analogous thing involves this extra bit, which is gamma mu. And this d mu will turn out to be very important. It's always this combination. When you are pushing something to a neighboring point, d mu is what appears. Okay? And in fact, gamma mu tells us how the basis vectors in neighboring vector spaces are related. Because the need to mix the components arises because the basis vectors are changed. And gamma mu actually connects a series of vector spaces along a path. Because suppose I ask you, how are the bases here related to the bases here? I can't do that in one step. Because all I have told you is how to do this displacement for an infinitesimal displacement, right? So to go from here to here, I cannot go in one step. I have to do by infinitesimal displacements and add them up or multiply them together, do the transformations one after the other. So I have to choose a path from here to here, chop it up into many pieces. For each piece, do the transformation as I have described just now, and then add it all up. Now, hidden here is going to be a problem, which I will come to at the end of today's lecture. Namely, the end result may be dependent on path. Okay? Because to go from here to here, I don't know how to do that globally. I only have a representation that tells me if I transport by a little bit, I know how to do. Another little bit, another little bit. So in other words, I have to add it all up. But if I add it up along this path and I add it up along that path, it may or may not be the same result. Okay? That is something we need to consider. Well, I'll come to. Okay? Just like when we discuss potential energy and work, you say, what is the potential energy at this point compared to the potential energy at this point? What you try to do normally, you say, I calculate the work done to go from here to here. But the work done is only defined for infinitesimal displacements, f dot delta x, right? So we add it up. No guarantee that when you add it up here and add it up there, the answer will be the same. And if the answer is not the same, you cannot define the potential energy. Okay? Same idea. Right, so now let me give you precisely the relationship between the connection 1 form and the basis vectors. So let me try to recall the translation operator. Suppose my convention may have gone backwards, but doesn't matter. Suppose I want to shift the black wave function or the black function to the blue function by this displacement of 0.1, let's say, just an example. So the blue function, which I call the displaced function, its value at 1.0 is the same as the value of the black function at 1.1. And in general, the value of the displaced function at x is the same as the value of the original function as x plus c. Okay? So you do a Taylor series expansion, you get this is e to the c derivative acting on f. So that's something we have discussed already. So displacing a function this is an exact to all orders in c even. This does not even have to be infinitesimal. But what do you do when you displace a vector function? Okay, so the same idea. I originally have a vector field, which is A of x. I define a new vector field, which is a displaced vector field. Obviously, what you do is the displaced field at x is the original field at x plus c. Right? It's the same idea. Just change the argument that's being displaced. Now, at any point, I want to expand the basis vector, the vector in terms of the components and the basis vectors. So I write this vector as the components times the basis vectors. Okay? But both the components and the basis vectors are dependent on position. For example, the basis vector here and the basis vector there are not the same. Okay? And of course, to expand any vector, I expand this vector in terms of these basis vectors. I expand this vector in terms of these basis vectors. So I expand this field at x plus c in terms of the basis vectors at x plus c. And the expansion coefficients are then, by definition, the components at this point. Okay? So that is straightforward. So in the same idea before, let me just do it to first order. So to first order, I just do a Taylor expansion. There are, of course, two terms. One term coming from the differentiation of this guy. So I have c mu, d mu acting on the components. The other, it acts on this guy. Okay? And I just called this dummy index J. Okay, so that's just a Taylor series expansion to first order, but noticing that the function that you differentiate is a product, therefore you have two terms. Right? So you see the key idea, where's the cursor, is that now you have to differentiate the basis vectors. That is the new ingredient. If the basis vectors are constant, which means either you have a Cartesian system or that there is no private vector space, all right? That there is only one global vector space, then the basis vectors would be constant and you won't have the second term. So the trick comes from the second term. Okay. And clearly, comparing with the previous result, I want to identify this whole thing as d mu, right? Because I said that normally for a scalar function, you only have the partial derivative. And now the whole effect I want to define as d mu. This will make it look like this one, except for a sign. Let's say this. Okay. Look like this, except that you replace the little d by capital D. So the definition of D is just to make it notationally convenient that when you deal with a vector function, the displacement is executed by the operator capital D. So let's see what happens to capital D. So we have capital D acting on A is given by this. I just copied the previous line. Okay? So capital D acting on A is little d acting on the components plus the derivative of the basis vectors multiplying A. Now, let me look at the thing which is new, which is this derivative, this second bracket. What can we say about this thing? D mu Ej. Now, notice there are two indices. They are different. Mu is an index associated with a base space. J is an index associated with a vector space. Okay? So think of d mu as just a subtraction between neighboring points. So I'm comparing Ej at 2 points. Let me just erase this. I'm comparing two vectors at x and x plus delta x. This is what I'm doing. All right? And this must be delta x mu d mu of Ej to first order. That's the idea. All right? What can I say about d mu Ej? Well, d mu Ej, you look at this expression, is a difference between two vectors. So it must be itself a vector. So it can be written as, if it's a vector, then I can write it as a sum over the basis vectors, right? So d mu Ej must be written as, Pi Ei. Okay? Since it is a vector, I can always express it as a linear combination of the basis vectors. Except that I notice that I have to label this with these two indices which appear. Okay? So this boxed equation, all it says is that d mu Ej is a vector, therefore it can be expressed as a linear superposition of the basis vectors. The superposition coefficients are P, and the index I is to be summed. The two lower indices, you just keep the two lower indices. They are free indices corresponding to those on the left. Okay, so I define a new object called P with 3 indices defined like this. And I put this in. Then I get capital D is little d plus P I mu J E I A J. Now I have chosen all the indices such that the vector index is both EI. So I copy out, pull the EI outside. I get this. I repeat this equation. So d mu A is this bracket EI. So perhaps I've gone a little bit too quickly there. So d mu A, if I am to look at its I component, it is equal to d mu acting on the I component of A, d mu delta Ij acting on the J component, right? I just rewrite the first term by inserting a Kronecker delta, plus P mu, mu. I should have inserted one more line, okay? So I just insert a delta Ij here, turn this into a J, and pull the two Aj's outside. And I call this d mu identity plus P mu Ij acting on Aj. Okay? So delta ij I write as the ij component of the identity matrix. And P mu I think of as a matrix P mu with entries ij. So that then tells me, if I just look at this, that d mu is equal to ordinary d mu identity plus P mu. Think of this as a matrix equation. Okay? And usually we don't bother to write the identity. But that is exactly, but we had derived earlier that d mu is derivative plus gamma mu. Okay? So that shows that the object P that I introduced is exactly the gamma. And since I define P by this expression, I now have this understanding of what gamma is. The connection 1 form in terms of basis vectors is this thing. Okay? The connection 1 form comes about and can be calculated if you know how the basis vectors change with respect to position in base space. So that is another definition of the connection 1 form. Okay? So I introduced the P, and I eventually discover that D is derivative plus P, and therefore P must be identical to gamma. Right? Because the basis vectors are changing, that's why you have to mix components when you have to displace. Any questions? Now, I have introduced rather general notations. Let me go back to the case of electromagnetism and how all this works out. Now, in the case of electromagnetism, the group is abelian. Remember, the internal group that we discussed has this general form, EI theta A T A. That is the internal group that we consider. TA are a set of matrices, Hermitian matrices, and theta A is a set of parameters. Right? Think of SU2, then A would take on 3 indices, 1, 2, 3, or X, Y, Z. Okay? But what about EM? In the case of EM, all we are talking about is just a phase transformation, right? E to the I theta. So that means there is only one non-trivial matrix, namely the identity. I should have written identity rather than 1. And theta A is just theta. Okay? And what is gamma mu? Gamma mu is an n by n matrix, which is anti-Hermitian, right? Now, in this case, n is equal to 1. So it's a 1 by 1 matrix which is Hermitian, which is anti-Hermitian. A 1 by 1 matrix is just a number. Anti-Hermitian means imaginary for 1 by 1. So in this case, gamma mu is just an imaginary number. So I just write it as I times a real number, which I call A mu. And just by convention, let me extract a factor E over H bar. All right? So that the A mu will in the end turn out to be related to what we are familiar with. Okay? The only point that we need to deal with here is just it is I times a real number. Okay? Because it is an anti-Hermitian 1 by 1 matrix. All right, so let's see what happens when gamma mu acts on a wave function. A wave function, in this case, is just a complex number, psi 1 plus I psi 2. Gamma mu is I times A mu, psi 1 plus I psi 2. So gamma mu acting, so if I write this in matrix or vector notation, I write the wave function as a column vector, psi 1, psi 2. You see what happens? The real part I call the first component. the real part on the right-hand side is -1 times psi 2, right? Never mind the stuff that goes, never mind the E over H bar A that I pull out. The real part of this expression is minus psi 2 and is related to this -1, okay? So it is minus, so the first component is -1. Oh, sorry, this is of course misprint. One don't change it. This is of course a 2. This is of course a 2. Okay. -1 times psi 2. And the imaginary part here is just 1 times psi 1 because of this I here. Okay. So it's 1 times psi 1. Okay. So this is a way of writing the relationship by showing the i's. This is the equivalent way of writing the same expression without showing the i's, but showing each complex number as a column vector of rank 2. I simply means mixing the real, turning real into imaginary and imaginary to real. And that's why it is represented by this off-diagonal matrix. In fact, think about a multiplication by I. Multiplication by I turns real into imaginary and imaginary to minus real, right? Okay? And that is why one of these has a minus I, okay? Multiplication by I turns real to imaginary, imaginary to minus real. So let me call this matrix epsilon. It is an anti-symmetric matrix. So in matrix representation, now this is actually a matrix, of course. It multiplies a column. So the IK component of this matrix is this stuff times epsilon IK. Epsilon is this matrix. Is that all right? So under a coordinate rotation, a phase rotation, that is what happens, and the corresponding gamma is given by this. Can be written in this form. And this I've already talked about, that I implies mixing real and imaginary components without changing the length, and gamma mu is anti-Hermitian. Okay. So the connection 1 form, in other words, gamma mu, can be written either as this or as this. They are equivalent. Okay. The epsilon is just another way of writing I. Okay. Epsilon with a -1 to 1 just tells you change real to imaginary, imaginary to minus real. And writing it this way, in the latter form, makes it clearer how it relates to the representation that will be more general, namely you write it as gamma mu ik, that the connection 1 form has 3 indices. The reason I want to discuss all this is the following. In general, the connection 1 form has 3 indices. But the simplest example, the connection 1 form is just A mu, or more properly, IA mu. So you may think somehow it seems to have only 1 index. And I just want to explain that the 2 missing indices are actually just in the factor I, which can be represented at this anti-symmetric matrix epsilon, which carries 2 other matrices. And the vector potential tells you how to transport a wave function along a path. Now, I haven't actually proved that if I write it this way, this A mu is the vector potential you are familiar with. Okay. But that should be obvious as we go along. So what we have established in this example is a very deep relationship between a concept in physics and a concept in geometry. That the vector potential A mu is something we learn about in physics, related to electricity and magnetism and so on. And the idea of a connection 1 form is one of the deepest concepts in geometry. Okay? And they are really one and the same thing. Yeah?
For this example, is the capital N 1 or 2?
Depends on your view. I mean, you can think of the vector space as a one-dimensional complex vector space or as a two-dimensional real vector space. The two views are, of course, equivalent.
In just general relativity, the gamma mu can be constructed from the metric. In here, the indices are different, so it is not possible
to connect. That's right. That's right. It's not. So general relativity or differential Riemann geometry is a very special case of this, where the vector space is a tangent space. It has the same. You see, in that case, the vector space you're talking about is deeply related to the base space. It is really the space of infinitesimal displacements on the base space. Okay, that is a very special vector space, and for that special vector space, you have something extra. And I want to disentangle that extra bit, which is special to that case, from the general discussion, which does not require a relationship between the vector space and the base space. And it is the general ideas that will apply to EM, will apply to non-abelian gauge theories, quantum chromodynamics, for instance. Okay, so that is a special case. Right. So let me now talk about non-abelian gauge theories. And I will use the example of SUN, which is the most important one. And in particular, you may want to think about n as being equal to 3, the 3 colors. So I have a field which is describes the amplitude of finding a red quark, green quark, blue quark. Okay, so that is the vector I'm going to deal with. This will be, in fact, a 3-dimensional complex vector space, okay? Because each entry can be complex. In field theory, actually, whether a field is real or complex is related to the fact whether the associated particle has an antiparticle, which is different. Okay, if it has a antiparticle that is different, then it's a complex field. But that's something we can't prove at this point. Okay, so what we have is a wave function, which is a column vector with n dimensions. The sort of transformations that I will talk about are these. Now notice I am now assuming that I can make coordinate dependent transformations. I can make local transformations, all right? Which is a generalization of this, well, just like this. So I'm going to do a transformation like this. And A ranges from 1 to n squared minus 1. Remember, because if this is an n-dimensional vector, the transformations have to be n by n matrices. They are n squared such matrices. So I have n squared TAs. I choose T0 to be the identity. And now I exclude T0. If I don't exclude T0, that is called UN. I exclude T0, it's called SUN. Okay? That we have discussed in an earlier chapter. And gamma mu is an n by n anti-Hermitian matrix. Now, if I recall the EM case, I had shown that gamma mu should be written like this. In that case, gamma mu is an 1-by-1 matrix. So it can be represented as a number. Okay? And the fact that it's anti-Hermitian means I insert an I here, and then this is real. So in exactly the same way, the generalization is now the following. This is an n by n matrix. Since it is an n by n matrix, I can write it as a sum over the basis matrices. Okay? So gamma mu is an n by n matrix, therefore I can write it as a sum over the basis matrices. Okay? The coefficient of the basis matrices I would call A super A. So this depends on X, this depends on X. Okay? And since this has a mu index, this has a mu index. Because there are a number of different t's, I now introduce an equal number of different a's. A's are the coefficients that multiply the t's. The t's are the generators. You must have as many a's as there are generators. Okay? The t's are just the basis for the set of all matrices. They are constant matrices. So you now are forced to introduce a set of coefficients. And just by convention, I just put down a factor here, G over H bar, where G is analogous to the electric charge. It's the coupling constant for gauge theories. That's just a convention. Some people don't even write it. Then you redefine the A. And then you put an I here. Why? Because this is anti-Hermitian. This is Hermitian. So if I put an I here, the rest would be real. So these are real fields. Okay? Because the TAs are Hermitian. Up to now, that's just a definition of the A's. So instead of, in other words, I can, because gamma mu is an arbitrary n by n matrix, which depend on x, right? So in general, to describe how the connection goes, you have to give me n by n, an n by n matrix. So instead of telling you what the n by n matrix is, I tell you what these functions are. Okay? And they are n squared minus one of them. Okay? So instead of telling you what the matrix is, I give you a number of coefficients that tell you what the matrix is. That's all. So that defines a convention for telling you what gamma mu is. So I've now introduced something analogous to the vector potential in EM, but carrying an index, TA. How many A's are there? Well, for the case of SU2, this would be 3. For the case of SU3, this would be 8. In general, SUN would be n squared minus 1. Okay? SU2 would be like rotations. So you have 3 generators like JX, JY, JZ. Okay? SU3, there would be 8 generators. And in fact, in one of the problems, I don't know whether it's one of those I assigned to, for next week or thereafter, actually I wrote out the 8 generators for SU3 for you and asked you to find something. Okay? They are 8 3 by 3 matrices. So what we have led to is that there are now n squared minus 1 so-called photons. These objects, these fields, they are n squared minus 1 of them. They are analogous to photons, and technically they are called gluons, all right, in SUN theory. They are things that will have a property very similar to photons, but they are n squared minus 1 of them. In the case of SU3, there are 8 different kinds of gluons. This is mathematical. Let me just draw you a picture. Perhaps that gives you a better view of what's happening. Suppose you have an electron scattering from another electron. Okay? How do we represent that in field theory? I don't have a different color. This color. Well, normally we say it exchanges a photon. There is only one kind of photon because it couples only to charge. Now, in quantum chromodynamics, what happens is the following. You have one quark scattering off another quark, the analogous diagram, all right? But quarks have colors. So, say a red quark turns into a green quark. Then this photon or gluon has to carry 2 indices. It is called a, let's say, if it goes this way, it is a red-green bar. So that color is conserved at this vertex, right? At that vertex, red becomes green plus red-green bar. So gluons carry 2 color indices. And if there are n possible colors, there would therefore be n square possible gluons. Now, the -1 means that the trace doesn't matter, that there is no gluon that corresponds to red bar plus green bar plus blue bar. That one you don't have to count. Okay? Now, that's slightly technical, but I just want to explain how the square comes about from the point of view of a picture. Why there are sort of 8 or 9 gluons and not 3 when in SU3. Because it talks about the scattering, quark-quark scattering. And when you have 2 quarks, you have 2 indices. That's all there is to it. Now, we have a lot of indices, and I want to make sure you don't get confused. There are 3 types of indices that we have to deal with. One I call mu, that is an index in the base space. So if you have 4-dimensional base space, M is 4. Tells you how many dimensions you need in base space. Then you have the vectors, which are n-dimensional. In SU3, this is n. And then A tells you how many generators there are, and in fact it's n squared minus 1 to be precise. Okay? So A runs from 1 to n squared minus 1, I runs from 1 to n, and mu runs from 1 to m. They are all different types of indices, not to be confused. Okay, so that is really all I have to discuss today for this chapter. I have introduced, by generalizing the idea, I have put together 2 ideas. One is the idea of internal symmetry, meaning I do a transformation on an n-dimensional vector. The other is a local transformation, so that the theta or this thing, this is actually what we used to call theta, really. Is position dependent, and I put the position dependence here, and therefore I introduce n squared minus 1 vector fields, and these will turn out to be the gluons. Any questions? Oh, we are again much ahead of time. I can always go on and talk a bit about.
Can you remind me again, why do you have to remove the extra the case of relation?
Yeah, because they are really 2 independent groups. Because UN factorizes into U1 and SUN. The set of you have a transformation that looks like this. Now, originally, you have something that goes from 0 to n squared. Okay? Well, this is, of course, a mathematical identity. I separate out the 0 term. But the point is the following. This factor and this factor commute. Okay? Because identity commutes with everything. So e to the I this can be written as e to the I this times e to the I this. These are 2 subgroups. This group closes upon itself. Okay? Because you multiply 2 of these together, you get another one of these. Okay? Well, we have proved this before. Has to do with the fact that the commutator of 2 t's is again traceless. And therefore, the 2 groups are totally separate. There's no reason why they should be mixed. Now, this is another concept which is similar but not the same as something we've talked about before. When we talk about representations, I introduced the idea of irreducible representations. You can have a big representation, say x squared, y squared, z squared, x, y, and so on. So you have six functions, but you can actually break them up into 5 plus 1. so that under all rotations, the 5 mix among themselves and the 1 mix is totally independent, right? So they have nothing to do with each other. They are called irreducible representations. In this case, this is a group, but it's actually the product of 2 groups, which have nothing to do with each other. They are subgroups, okay? And there is no reason why the 2 should be related. So these are, I don't know what it's called, irreducible subgroups, some terms of that type, okay? So we always look at the irreducible subgroups, and that means you look only at SUN. So you remove the identity matrix.
Is this related to the gluon always color singlet?
No. Color singlet is still within SUN. Still in SUN. Now, I'm being heuristic here, but to do it properly, you have to write down the equations. Right. If you have no questions, perhaps I can go on. I can go on a bit. Let's see, where are we? Okay. Now let me talk about the concept of curvature. Okay? And the change of basis. 3 simple concepts. Now I have said that the gamma mu connects the vector spaces along a certain path. So if the connection is independent of path, then all the vector spaces can be patched together consistently. And I actually don't need to have different vector spaces. Now, let me explain this somewhat more carefully. Now, suppose I have my basis here like this. And the basis here is patched together and it becomes like this. If this is independent of path, then I can say the basis here is like this, the basis here is like that. I don't have to tell you which path. That is the rotation involved. And I don't have to tell you the path. Okay? So you rotate by this much. Then I can simply rotate this back. Right? Then this vector space will be the same as this vector space. Okay? Now, once more. Gamma mu tells you how this vector space and this vector space, how they are related. So if I know the answer, I can rotate this back and I have the same basis vector. Okay? It's not enough that I can rotate a neighboring point back. Suppose I have basis vector here. How much do I rotate this one back so that they are the same? So I have to tell you the rotational relationship, the linear relationship between this basis vector and that basis vector. Well, how do I do it? I use the connection to take me from here to here to here to here, all the way to here. I add it all up together. I know how much to rotate this back. Except if this answer is path dependent, I can't do it, right? If it's path independent, then I can say uniquely the basis vector here is like this. Here is rotated by this linear transformation. I transform back. Then all the vectors, basis vectors are the same everywhere. So although you have different vector spaces, all the different vector spaces have the same basis vectors. They're identical. If they're identical, I don't need to bother. I can call them one single vector space, and it would be trivial. Okay. So this whole idea of private vector spaces is non-trivial only if doing this is independent of path. Okay? If it is dependent on path, we say there is curvature. If it is independent of path, we say there is no curvature. Then by a change of basis, we can return it to one single vector space. No need to bother. So we are going to investigate the difference between different paths when we transport a vector by parallel transport. Okay? So an equivalent statement is whether or not parallel transport of a vector around a closed loop reproduces the original vector, because this argument you are familiar with when you talk about work and so on, right? Whether the work along two different paths is the same statement as whether you do work around a closed path, you get zero. Same idea. Okay. All you need to do is to check for rectangular loops. That, again, is the usual statement. Whether a line, this is like whether a line integral around a closed loop is zero. You only have to check around for small loops. So here's the same idea. I only have to check for rectangular loops, and namely the following. I start at this point. I displace by Cassi. I displace by eta. I displace by minus Cassi, I displace by minus eta. If I do this closed loop, do I get the identity? Okay. Now, if I displace by Cassi, then the operator is e to the Cassi times the covariant derivative, right? So that is the first operator. Okay. A is the operator for the Cassi displacement, or e to the a is the same. Then B is this guy, is eta times D. So this takes me by Cassi, this takes me by eta. This is the inverse of this transformation, because I go by minus Cassi, so it's e to the minus a, and then I do this, is e to the minus b. Is that okay? So schematically, that is how you go around a loop. But of course, A and B do not commute. If A and B commute, then of course this is just the identity. That's the whole point. Now, so what we have, the overall result is this. EA, that you read these operators from right to left, right? Because this is the first operation that you do. EA, EB, E minus A, E minus B. And now, A and B are both infinitesimal, okay? Because Cassi and eta are infinitesimal. And you see that if either Cassi or eta, either one of them is zero, the result will be the identity. Because, think about it, if Cassi is zero, that means this is nothing. So of course, this displacement is identity, that displacement is the identity. But if this is zero, these two lines collapse to one line, right? So in the same place you go up and then you come down, of course it cancels, right? That just means mathematically, if Cassi is zero, then e to the a, e to the minus a you can ignore, because these two are identity, then EB, E minus B, of course, will give you zero, right? And likewise for eta. Therefore, the departure from identity, the leading term must be proportional to both Cassi and eta. So the overall result for the loop must be depart from the identity by something which is proportional to both Cassi and eta. Because if either one vanishes, you get the identity. Which means, since Cassi appears only in A, and eta appears only in B, I can also say only to order A times B, not A and B. Okay? Must be proportional to A times B. That's number one. Number two, if A and B commute, then you would get the identity, right? So obviously, this must be of order not just A times B, but the commutator of A and B. That must be the leading term. In fact, it must be, the leading term must be this times a coefficient, right? And I claim it is just A minus A times B. That is the leading term. Okay. Now, go from the first line to the second line. Just a matter of multiplying it out to second order and checking that, and making sure you don't swap factors around, right? making sure when you have A, B, and BA, don't confuse them. And you don't need to know anything about what A and B are. Okay? A and B are just anything. Any two operators that do not commute. Calculate to lowest order, expand it, and this is what you find. Okay? I am just giving you a heuristic hand-waving argument as to the form of this to indicate that all you need to check is that this coefficient is -1. Before you do anything, you know that there won't be terms like A squared or B squared or AB, the product, but not in the form of commutator. Okay? Just a simple guide to doing, this is not a very complicated calculation, but if you think about it a little bit and anticipate, you can guess the form of the answer, more or less, before embarking on the calculation. Okay? So just a matter of multiplying it out. Right? I won't spend time doing it. I think this is even one of the exercises. But, okay? Any questions? So writing out what A and B are, A is C times d mu, B is eta times d nu. The overall result for the loop to leading order in the size of that rectangle, because C times eta is just the size of that rectangle, right? Is given by this commutator, which is the commutator of d mu and d nu. So it is an object with two indices in the base space. This I call the curvature. The curvature is the commutator between two covariant derivatives. And it has two indices because the derivative index along base space, right? So it is the difference between this covariant derivative and this covariant derivative, the commutator. So a curvature is a matrix with two indices. So think about the base space being space-time. Mu is 0, 1, 2, 3. R mu nu would be 16 objects. Each of them is a transformation of the vector space. So each of them is an n by n matrix. For the case of SU3, this would be a 3 by 3 matrix. So let me write it down. So take the case where you have the base space, which is space-time, and map to a vector space, which is n equals 3, say color. Then R mu nu would be 16 matrices, and each matrix is a 3 by 3 matrix. All right? Any questions? But of course, the 16 matrices are not all independent, because by definition, R mu nu is antisymmetric in the mu nu indices. Okay? These two indices are antisymmetric by definition, because it's a commutator. Right? So that introduces the concept of curvature. And if you, I think I have a next slide. No, I will have it later. But if these are matrices, that means I can give them indices ij, right? So mu nu runs from 0 to 3, and ij runs from, say, 1 to 3. So this is space-time. This is the vector. So if you write out the elements of this vector, of this matrix, the curvature is an object with 4 indices. Okay? 2 indices for the base space, 2 indices for the vector space. Now again, for those of you who have studied relativity, the curvature tensor in that case, all 4 indices are the same type. Because in that case, the vector space is the same type as the base. And you also see why you have 1 up and 3 down, in the sense that these two are both down in the following sense, that d mu are both lower indices. And these two, one up, one down, because we want to write it when it acts on, you get something like this. Let me suppress the mu nu indices. The R matrix acting on psi, its I component is Rij psi j. So if you want to maintain the convention that you multiply, do the summation convention only on one up and one down index, then the Ij indices should be one up, one down. Okay? And the two mu nu indices are both covariant derivative indices. And they are the same type, so they are typically written both at lower indices. Okay, so that is R mu nu. But let's write out what this actually is. The covariant derivative is ordinary derivative plus gamma. That's the general definition. So if I calculate the commutator, is derivative plus gamma, derivative plus gamma. Now, just to make sure you understand this, let me just work out one term. For example, what is this? Okay, so there are four terms, actually. Now, this and this would be 0. Ordinary derivatives, they commute. That's just the usual statement in calculus. That's mixed second-order derivatives. Doesn't depend on the order of the derivative. So there are four terms. One of them is this d mu with this gamma nu. Let me deal with that one first. The way you should think about these commutators is to imagine that it acts on a wave function psi. Okay? So what does this mean? This means del mu gamma nu minus del nu gamma mu. Oh, sorry, the other way around. Think of it as acting on a wave function psi. All right? What that means, when you write it this way, is that the del d mu acts on the product, whereas this one is only this. So when you take this derivative, when this operator hits the psi, that just gives that term. So the remaining term is del mu acting on gamma nu multiplying psi. Okay? So the derivative on the gamma. So you just erase the psi at the end. Commutator of d nu and gamma is just the derivative of gamma. Okay? So you have the derivative of gamma nu, and then the opposite one, derivative of gamma, but with a minus sign because it's backwards. And then the fourth term is gamma mu, gamma nu, commuted. So R mu nu, more explicitly, is the following expression. It's the derivative of gamma, the anti-symmetric derivative, plus the commutator between two gammas. Now, because the two parts are slightly different characters, that's why typically we write it out explicitly. Derivative is a derivative operator. Gamma is a matrix. It's an n by n matrix. Okay. So the first one is sort of like the curl of gamma. The other is the commutator between two gammas. Now, for those of you who have, again, learned the analogous expression in general relativity, you should probably recognize this. But this is written in a much more compact form, okay? Because there are two indices which I have hidden by writing as a matrix. All right? Otherwise, I should have an Ij here, Ij here, Ij here. That's okay. But here I have hidden more than two indices because I have an Ij on the outside. But when you multiply two matrices, there is also a repeated thing on, that is summed. Right? So here I have actually hidden three indices by using the matrix notation. Do you understand? Maybe I write this out slightly more carefully. What you have, R mu nu, this is a matrix with entries, let's say Ij, right? Is then equals to del mu gamma nu, matrices Ij, del nu gamma mu. Matrices are index ij. Now, this is slightly more tricky. This is gamma mu minus gamma nu, gamma mu. And this is ij. This is ij, okay? Let me just write out this one. When you have the index for a product, the first index goes with the first product, the second goes with here, right? That is how you multiply two matrices. And then when you multiply two matrices, the indices right next to each other are summed. That is the usual rule for matrix multiplication. Okay? And likewise for that one. Okay, so what you have, let me just copy this down here. So this is plus gamma I mu k, gamma k nu j minus gamma I nu k, gamma k mu j. Okay, I think this is the expression that you learn in general relativity. All right? Except that in that case, all the ijk's I would also write as Greek indices because they are the same. And it looks very messy, and I am sure after the exam, you can't remember how the indices go, right? Especially in the two gamma terms, it's a big mess. Okay? All I'm saying here is that if you regard R and gamma as matrices, and write a matrix equation rather than an equation for the matrix elements, it is very easy to remember. And if you want the details, you can always fill it in by putting in how naturally matrix multiplication goes. And of course, it also helps. You see, I'm talking about slightly more general case. And it actually helps you understand. Because in the more general case, I distinguish between two types of indices. It's the ijk indices, which are handled like a matrix and a vector. Okay? The mu nu indices you just carry along. It tells you what is the difference between d mu, d nu, the two directions in base space. Historically, it's very interesting. Historically, actually, the whole idea of Riemann geometry came first. And Riemann came up with this expressions such as these, rather messy expressions. And it was some years later that people actually understood it in a more general context and introduced these ideas. Now it's much easier to actually understand what's happening. So we have this n by n matrix equation. And if it's a matrix, that means this matrix acting on psi, the I component, is a linear combination of psi j. So I introduce indices ij. Okay? So R has 4 indices. 2 of them are like ij. In other words, they are indices in the vector space. 2 of them are like mu nu. In other words, they are indices in base space. Okay. Now, let's go back to the case of EM. Remember, in the case of EM, gamma mu is just I times a number times the vector potential. So what is R mu nu? So it's this derivative. If I just pull out this factor I over h bar, the derivatives is just d mu a nu minus d nu a mu. Now, this term is actually 0 because the gammas are just numbers. They are 1-by-1 matrices. All 1-by-1 matrices, of course, commute with each other. So there is no commutator. That term is 0. That is always true for abelian fields. That is when the operators commute with each other. So what do you have? This bracket, of course, is just the electromagnetic field tensor, F mu nu. Okay? Because if you, for those of you who haven't studied relativity, just look at the spatial components. Look at, say, 1, 2, F1, 2. That would be D1A2 minus D2A1. That's curl A, third component. So that's B. Okay? And in fact, let me do the other one perhaps. I think there are a few of you here who did not study relativity, although most of you did. We just do this one. F12 is D1A2 minus D2A1. That is curl A, third component. That is the third component of B. Let's say F01 is D0A1 minus D1A0. Now, let's be a little bit careful. D0 is dA1 dx0 minus dA0 dx1. Okay? But A upper 0, 1, 2, 3 is the scalar potential and the vector potential, right? But A upper 0 and A lower 0 differ by a minus sign. Because when you raise a 0 component or lower a 0 component, that costs you a minus sign. So this is minus d dt of A1, plus d dt of A1 plus d phi dx1. So this is gradient phi plus dA dt, one component, which is minus E1. Okay? So up to minus signs and so on, F, the tensor F mu nu just captures the electric field and the magnetic field. And this statement that F is equal to this anti-symmetric derivative is just a generalization that of B is equal to curl A. Okay? So this is a generalized curl in 4 dimensions. A curl is just an anti-symmetric derivative, that's all. Okay? So I think I have this on the next slide. Oh, well, actually I have this here. Okay. So F12 is B3 and F01 is E1. Here I calculate 01 upstairs. It's the same thing. Okay. Earlier I showed a relationship of the vector potential and the connection 1 form. Right? In the earlier slide, which is similar, the upper portion was A mu, the electromagnetic potential as a concept in physics, and the connection 1 form as a concept in mathematics. Now I take this one step further. I tell you the electromagnetic field in physics, E and B, is related to the concept of curvature in mathematics, which is R mu nu. Okay? So let me put this slightly more graphically. Go back just to EM. I have a complex plane, which means I have real axis and imaginary axis. So I can rotate this way. That's a phase convention. So I change the phase convention as I go here. I change the phase convention as I go here. That introduces the concept of d mu, d nu. If these two processes do not commute, then I get an electromagnetic field. Electromagnetic field has to do with the fact that if I change the phase convention this way, and I change the phase convention this way, the two processes, if they don't commute, then there is a non-trivial electromagnetic field. Right? So this is a deep connection between very key concepts in physics and very key concepts in mathematics. Right? The concept of curvature of connection 1 form is now sort of the starting point of all the discussions in Riemann geometry of fiber bundles and so on. And this is the relationship I want to establish. Now, here, I think the next bit is, okay. So there is a non-trivial E and B if and only if the complex planes fail to patch together trivially. The next bit is going to be a little bit, the mathematics a little bit more messy. I don't think I would want to start today. I would urge you to read this up first, and then I will cover it next time. And then after we've done these, This is all a little bit abstract mathematics. Then we will come back to a couple of topics which will be a little bit more physical, because we will come back to the case of EM to deal with a number of concepts and consequences that arise from these things, right? Like flux quantization, monopoles, Aharonov-Bohm effect, whether A is real, and so on. Those would be slightly more physical. For the non-abelian gauge fields, except for this last bit, which I will discuss, it is rather more difficult to tell you more, because there is one ingredient that I have deliberately kept away from this series of lectures, and that is the whole idea of Dirac spinors. I have used everywhere examples from quantum mechanics. In quantum mechanics, if you have an electron is just psi, just one complex number. You can have spin up, spin down electrons. So that is a two-component object. But actually, in relativity, you have to talk about a four-component object. Roughly speaking, it means electron spin up, electron spin down, positron spin up, positron spin down. Actually, even that is not quite right, because obviously they have different charges, so how can you put them together in one column vector? The idea is that if the two upper components are annihilation operators for the electrons, then the two lower components are creation operators for positrons. Okay? So roughly speaking, it goes like this. You think about, in a second quantized field, a psi that really is, let's say, a destruction operator for a spin-up electron, a destruction operator for a spin-down electron, a creation operator for a spin-up positron, and a creation operator for a spin-down positron. Okay? This object, all four components carry the same charge, because acting on something, they always increase the charge by 1 unit, either by destroying an electron or by creating a positron. And really, in quantum field theory, the wave function that you deal with should be this kind of thing. That mixes, that talk about at the same time particle and antiparticle. Okay? And the reason, of course, is the following. Whenever you are in the relativistic domain, when energies are large, you have the possibility of creating pairs. Okay? So creating positrons is something you have to talk about at the same time. So you have to talk about these wave functions, which are twice the number of dimensions. That's not the worst part. Secondly, you can talk about them only in the quantized version, because you see I have destruction operators and creation operators. So you have to talk about the quantized, second quantized fields. And you have to marry all the concepts we have now, which is how to mix things up with this whole formalism before you can really write down the theory of quantum chromodynamics. Okay? So how do you generalize the quantum chromodynamics? Let me just... this is a red quark pointing up, red quark pointing down, red bar quark, anti-quark pointing up, anti-quark down. Okay? So this is what I mean by the red wave function. And SU3 then everywhere changes these three. Okay? So in the quantum chromodynamics, there are really two ingredients that we have to bring together. Well, actually three ingredients. One is the fact that you can swap these three indices, change the color. That's SU3. The second is that you can do this differently at different points. That's local SU3, or gauge theory of SU3, which I am beginning to sketch out for you, and I will finish as far as possible next time. But the third ingredient is that you are not just changing abstract things, red, green, blue, but changing these things. Okay? Only when you put the three together then you have the theory of QCD. But I don't think we have enough apparatus to talk about this sort of thing, where you deal with particle and antiparticle together in a second quantized field. Okay, so of the three ingredients, I will only be talking about two. Okay, namely, the ability to swap the three indices. Secondly, the ability to do so locally at each point, which will lead to the gluon fields. But I will not be able, within this class, to talk about the quark fields and what laws they satisfy and so on. Okay? Because the laws they satisfy are basically the Dirac equations, the quantum version of the Dirac equations, which I think you are not familiar with. And I don't think you can absorb several new concepts at the same time. That's why I put the quantized Dirac version, second quantized aspect aside, and just introduce the other concepts in this course. Right, any questions? We have a few more minutes. We are way ahead of time. Okay? Right, then let's break a bit early.